text. Yeah. And then it pops up with like username. Oh yeah. I'm good. Yeah. Yeah. He's the other. Yeah. He's the. Just go Google. Sweet. Anyone know the username for?
Guess.
Yeah, just guess with a small G.
Okay, guess
Small
the
everything.
Passwords, guess.
It's guest role, capital G, capital R.
Start in 10 minutes, I guess. Is that cool? And I've got goodies from O'Reilly. And I was going through my closet and found a vintage flux capacitor shirt that I've worn for the last 2 years, but it doesn't fit me anymore, so because it's a large. So that's the grand prize. It's been washed, you can see. That was from like years ago. Cause a frenzy, but Tensorflow that I stole from a Tensorflow training, so I'm going to pass them on to you guys. There's some beer food I think I spilled. Not anymore. Yeah. Yes, we're good, capital G. Yep. I think we're good, man. We'll start in a little bit. All right, pop quiz. This is for the t-shirt. And this plagues me every like 6 months. I get into this situation with GitHub, or with Git. And I can't ever figure out how to get out of it. It's that classic problem where like you can't reset, like you can't do the hard reset, and it still complains that I'm doing something wrong. So. Yeah, so this is what it's preventing me, and this is because I'm in through Kubernetes using the kubectl exec, not Docker exec. But if I do git status, it's saying they still have these things. And I'm just trying to, so yeah, what do I do? If I just want to clear these out, I already know that they're wrong.
Oh, you don't want any of those files?
Right.
So you could say, yeah, git reset hard.
Let me just make sure that I don't want
I
those.
think it's caps for hard.
Oh, yeah. I just want to double check that I don't need it. Because the reset wasn't working, which is why it was weird. Yes, I always end up, I just delete everything, or I copy it to temp or something. But there's got to be a better way. Someone please take this small size t-shirt off my hands. Or smaller size.
After the define where you want to reset that head to, you reset that hard or the define where in the timeline you want to reset it to, you reset that hard. So I think you do that.
Right. Right. But I don't think that was working either, but let me just double check.
Are you just trying to check out the last version, or?
Yeah, I mean, I just, like, I don't care about what's in my working folder.
And you've already committed the other one?
I see, it's hard to, let me, yeah, hang on. I actually do need that. Check. So it's saying I haven't concluded my merge. Merge head exists. Git status.
Do you want to stash it to use?
I stash them. That's the best thing to do, right? Use git commit to include. See, I don't even know. I mean, I should see those little like arrows, right? A little like here and here somewhere, I think. Well, I'm scared to do reset now because I actually do need these. I've given you guys an impossible problem because I really want to keep the shirt. All right. Yeah, the merge tool, for some reason, the merge tool is not coming up when I go through Kubernetes into the Docker container. It's weird. But I think if I go, anyway, it's not going to affect anything, so. I'm supposed to remind you guys that Strata's coming up in like 2 months or something, so buy your tickets. Anyone actually want this one? It's a Spark 1.1. It's like a vintage. I think this is before data frames. Yeah, that's how old this one. Yeah, Holden's working on a new one. And this is probably like one of the best books ever written. Yeah, Sean Owen and those guys are like working on a second version. Supply chain optimization. So let's get going here. Put the mic on. Who here is not sick, by the way? I'm like deathly ill. Well, not deathly. Really? You're actually
I'm over it.
feeling good? Yeah, did you just get over it? Seems like everyone sick. Yeah, we actually lost one of the speakers. He was more of a Mesos Spark guy, but he's actually working with Google and the last speaker for the Kubernetes and Spark integration. So same theme. And then next month, we're going to do pretty hardcore Mesos and streaming and hello. It's going to be a lot of streaming in the next 2 months. And then March for Strata, like I actually somehow managed, I think it was through this deal, to get a room at the conference center, at the San Jose Conference Center. It's free to come, like you don't have to have a ticket for Strata, but you can get in. So keep an eye out, that's the March meetup. And we've got Google Beam, like one of the leads on that group from Seattle. Everyone's coming in town for the conference, so like I was able to get them to agree to come. And then the Flink guy, right, like Jamie Greer, if you guys keep an eye on Flink, he's kind of their San Francisco proxy, right? So he just had a baby, but he's still gonna come. Let's see, let me pull up that here. I'm bringing Taxi back, by the way. That's fine. This is old school. I found all this stuff in my closet. When I got back from like traveling, I decided to clean one portion of my closet. But it was mostly the hats and the tech shirts. All right, so I've given up on slides, and I just basically Meetup as my new PowerPoint, which is really sad. We had 5,000 people. How crazy is that? How crazy is that? Thank you. Hit 1,000 people for the GitHub repo that powers this, right? The flux capacitor stuff. 6,500 DockerHub polls. This is just me grinding, going door to door, country to country, asking people to please star my repo so I can claim 1,000 stars. I'm really excited. If I do say so myself, I did a really good talk in Spain. And which is kind of cool because like I think people were afraid to ask me questions because of the language barrier maybe, so it's just like I could just talk and no one like said anything. But actually it was a really good talk. I got some good feedback. It's funny because people kept saying congratulations, congratulations, and like I thought like I won some prize, but that's their way of saying like good job. So I was like, where's my I don't know. All right, I'm not gonna actually play it. Tensorflow 12 came out. My buddy Sam, who some of you have probably met from the work workshops and things. He reminded me late last night that TensorFlow 1.0 alpha is out right now, so as not to embarrass myself and say that 12 is the latest. Actually, TensorFlow 12 is where a lot of the API changes happened and a lot of the like deprecations, right? Like in the preparation for 1.0. So 1.0, if you guys remember, I think Spark tried to do this, right? 1.0, where they claimed backward compatibility, and then again 2.0. That was a disaster. Spark 2 was a disaster. There was a really good blog post. I'm not sure if you guys know this dude, Pete Warden. He was acquired. His company was acquired. I think he's out of London or something. He's big into mobile TensorFlow. I think that's why they picked him up. But so he spends a lot of time thinking about what to do with your big bulky models, right? Like after they've been trained, and they have tons of nodes and tons of layers and dropout nodes and things that are specific to the training step that you don't need during the actual prediction, right? Like the inference side. So he announced there's this tool. It's called Graph Transform Tool. It's pretty cool. He's been sort of like blogging about these things. The first that we would have heard of it was the 8-bit quantization for mobile devices, right? Because that's his jam, is trying to get these big graphs down onto small devices. Yeah, so that's actually, I think he references in here, 8-bit ints from these big 32-bit floats, that kind of thing. So it's this graph transform tool. That's kind of the formal project now that's around this, and there's some really cool stuff here. It's sort of like how, and like these optimizations have been going on for years and years, right? Any kind of, graph like rewriting and constant folding and all that, but it's, pretty much like very similar concepts here. So yeah, the 8-bit quantization, constant folding, things, I mean, this sounds silly, but like getting rid of, your like summary writers, like during your training, you're always like writing things out so you can view it in TensorBoard. Yank those out, you don't need them for the inference side of things. Like renaming hops. Things like setting devices. So during training, you sometimes want full control over which device that your stuff gets placed on, right? GPU, things like that. But typically, when you're doing the actual prediction side, you don't have that kind of luxury, so you would yank out anything like that. Let's see. Yeah, so some cool things there. So this is the formal project. So keep an eye on that. Oh, and actually, I'm going to skip. Well, there's this project out of Netflix that kind of has its own life now. It's called Vegas Viz. Have you guys seen this or heard of it? Seen a video on it? There's a link off the Meetup to the video. It's kind of a strong statement, but they're sort of terming it Matplotlib for Scala. And they have the Zeppelin notebooks, and they're rendering some pretty cool things. Their whole jam is the ability to have interactive like graphs and charts and things. So yeah, keep an eye out for that. There's a cool video, actually from the Spark Summit, which somehow I missed that. I found out about this from a buddy from Netflix. But yeah, this part here. So actually, I just signed up with O'Reilly to do a video series and an online training thing. So they're moving more towards Safari as their online training platform. Or let's see, how do I say it? So before they were charging money, like they would charge $500 for like a 2-day course or something. They've been kind of playing with the different pricing models. And I think what's going to happen now is it's basically rolled into Safari, right? So just like any good VC, right, like they don't care about one-off. So they care rather more about sort of recurring revenue and things like that. So that's why Safari is kind of their primary focus. So yeah, just getting signed up. So yeah, I'm working on high performance TensorFlow, so that's actually going to be a lot of those optimizations, sort of post-training, and then scaling it out, some of the stuff I'm going to show today. And then I've got a second proposal out for distributed TensorFlow. So basically, Cloud ML, it's the Google Cloud ML service. I'm kind of secretly building that, even though it's not going to be anywhere near as sweet, I'm sure. But it's using Kubernetes, so you can drop in your TensorFlow models, it'll optimize them, and then serve them. Also got a demo here. I'm using Airflow. So I'm gonna train a model. I'm gonna, for this one, it's gonna be generating PMML. I'm gonna commit the PMML, and then that's gonna trigger an Airflow. You know, there's a webhook that comes in, and then Airflow kicks in and actually deploys it to both Google and Amazon as a canary, right? That's running alongside. So there's a lot of steps. And, you know, yeah, we'll see how far we can get. Also updated, if you guys remember, I have this Amazon. It's kind of like the Amazon AMI, except it's not specific to Amazon. That has, you know, Tensorflow installed. I believe it has the, you know, rather open gloss libraries and all that stuff installed. So it's, and then yeah, there's instructions on how to do it through Amazon here using the NVIDIA Docker. So I just updated this for the new P2, rather GPU instances. So here's the older G1s. So that's one GPU. There's the 4 GPUs. Here's the new ones. That's one. And then I left this running for like 2 weeks, and I got a big old $2,500 bill from Amazon for 16 K80s that I just kind of forgot about. You know, like who forgets that? And then I've got all the steps on like how to use it, how to get TensorBoard running. So this is actually kind of cool. So here's TensorBoard. I mentioned this before. This is during the training process. Oh yeah, this changed for V12 also, right? Like they added a bunch of new like visualizations and for like word embeddings and things like that. So this is multi-GPU training. So zipping through, this is some of the same stuff I had before. But here's the 16. Yeah, so this image cost me $2,500. So study it, please.
So have you noticed the things to be pretty linear? I think that's what they say.
Yeah, that's what's interesting. So actually, so the question is, going from 1 GPU to 2 to 4 to 16, is it what you would expect? And it's not. So, and some of it, I thought maybe, you know, wasn't allocating them all rather evenly. Maybe I was, you know, favoring one. One thing I did discover in that research was the first time things happen on a GPU. What's the term for it? Like there's a term. Basically, there's this like warm-up period. So you should always plan, if you have 16 of them, plan on like warming up all 16, right? Like before you start, right? So doing all of your like benchmarks and things like that. I think there's a term for it. I think I actually documented it here because it burned me. But yeah, this is kind of cool. So this is TensorBoard, and you can actually render all. So I trained with 1, 2, 4, 8, 16. And wrote them out to one parent directory, or each, and then I point TensorBoard to the parent directory where each of them live, and they actually render all nice and next to each other. Is that not the image? Anyway, but yeah, that's the legend, so just imagine it being a super nice image. I'm not paying $2,500 more for that. But here's how to get, so I've got Jupyter running inside of this, that Docker image. And got some examples, things like that. Okay, so this is all flux capacitor stuff on the right side. That's what I'm zipping through here. Sorry, that's making me sick. If you look on the right nav bar, you'll see GPU somewhere. I also restructured some of this over here. Yeah. Oh yeah, I've got Minikube working too. Has anyone used Minikube? It's it's like local Kubernetes. What's cool is, well, it's cool because things appear to start up, but then you realize that you only have 8 gigs of RAM or 16 gigs of RAM, and then nothing, you know, just kind of hangs. It's like, resources, you know, all these processes are dying, right? Like the killer, except it's your Docker killer. So, but yeah, there's steps on how to get that working. But some of the pipeline components, I don't have all of the full stack in there, but I've got, you know, DockerHub, and I've got things like that coming. All right, what else? I'm finally using Kubernetes labels, like a boss, actually. That's how sweet I am. So what's happening here is you can label a node, right? Like you would like label a node for like GPU, or in my case, I have actually 2 separate clusters. I've got a training cluster and a prediction cluster. So training is where Jupyter lives, and Spark, and all the batch slow stuff. And then the prediction cluster has been isolated, and that's all of the like Netflix open source and all that. Let me just show it quick. I think you guys have seen me talk about Weave Scope here. This tool is pretty cool. It's kind of a like visualization of your Kubernetes cluster. There's the Kubernetes dashboard, which is pretty badass. This actually, it's sort of like App Dynamics, where it has an agent that's running and knows all the traffic between all the different Docker containers and what's going on. You can actually click in here, so I can click into Jupyter. I can go to the specific pod. I can actually get on that pod. I can look at logs, or I can actually physically get on there. So I think this is the one I was having problems with. So if I do, I bet if I run a notebook here, it'll probably light up a little bit. No, didn't do anything. Anyway, but yeah, it shows you CPU, it shows you all the cool system stats. What's cool too is that you can actually scale up and scale down with this tool. So if you don't feel like using the command line for whatever reason, and you want to just press the up arrow and down arrow, they have that support as well. So, and you can, so I was going to show you guys, I have different nodes here. Let's see, hosts. So actually this Kubernetes cluster is made up of 3 Amazon nodes. I've never quite been able to figure out how that's rendered. Yeah, so one of the nodes is the training, one is the Kubernetes master, which is just a small, like M3 or something. And then I've got two 2x larges, R3 2XLs, 60 gigs of RAM each and 8 cores each. So you can kind of go look at how much available memory there is, that kind of stuff. So kind of cool. So if you label, and then when you go to deploy your pods or your like replication sets, replication controllers, what you do is actually specify where you would prefer to be. If it's Spark that I'm deploying, yeah, I want it to go to the slow training batch cluster, not the fast, fun Netflix prediction cluster. All right. Same with GPUs too, if you're deploying. Let's see. Keep things moving along here. I'll do quick intro, quick demo. Yeah, so I already talked about the next 2. There's going to be a lot of streaming. You guys want to hear about streaming? I'm not going to hear it today. It's fun. Prepare yourselves. Actually, I'm excited to be in South Bay again. I'm excited to see sunshine for the March one. I think February is going to be up here. Okay, so that's that. Let me do a quick demo. Then I'm going to give you a minute. Yeah, my friend Lena here, she has a really cool startup. I've been getting a lot of people, and I don't do this a lot because it's a slippery slope, but she has a really cool startup. It's probably education-based, has AI. I've been getting a lot of asks probably recently about if I know people that can pay them money to work, because I like people that don't need money to come work for me. Right? I like them to just come and show up at my house and write code, and I'll feed them some of my roommates' food here at work. But there's actually people that pay. You can pay?
Yeah.
Is that why you're here? Okay. So yeah, so we'll give Lena a few minutes. And you came in from where?
France. I'm from France. Yeah.
Very cool. But now you're in the city, right?
Yeah.
All right, so let me just do a quick demo here. So here's the webhook stuff. Have you guys played with these webhooks? It's pretty cool. GitHub, you can basically get to anything, right? Like any kind of events. If you make an organization private, you can actually get notified of that. And I was like, I don't know exactly when I would use that particular notification, but it's kind of cool. So let me hop over. I want to do this here. And then I want to show a cool load test too. I'm big on load tests. So let's see. And I could use JMeter, but that's kind of boring. especially because my laptop's typically the bottleneck. Oh yeah, one other thing too, in case you're playing around with TensorFlow, I found this. Yeah, so keep an eye on this dude, this Yaroslav guy. I saw him speak at a TensorFlow meetup like this summer, and he was going to disappear and go hiking for months and never come back to the Bay Area. And like January 1st, I saw his LinkedIn, he switched over to OpenAI. So OpenAI, pulled him in. He's super active on Stack Overflow. He answers every single question. He knows everything about TensorFlow. He was part of the project early on. He wrote this little show graph thing. You can actually, within your Jupyter notebook, render the graph and kind of play with it and figure out, look at the inputs, look at the outputs, look at various nodes. I did not get this working, which I was bummed about, but that's an exercise for you, the readers. So let me just walk through this real quick, and not necessarily run everything, but so picture this is from Jupyter notebook. We're using PySpark. For this case, we're pulling in so this is the Airbnb data set. We're doing both, what are we doing here? We're using continuous features, categorical features, slurping in all the data, building a model, and then we're going to deploy it. So here's all the fun vector assemblers, things like that. We're using linear regression. We're combining continuous with categorical. I don't know what that to do was. We're converting it to PMML and then pushing it out to the prediction servers. So here's an example of the prediction server running in Amazon. This is the actual REST call that's made. Passing in the fun XML. So this is the call update PMML. So this is actually, so there's two deployment models, right? There's the mutable deployment model where we're actually changing in memory, right? Like flipping the model. I saw that completely fail at Netflix. Yes.
Is this code, are you sharing it at GitHub somehow? Just so I know.
Oh, yeah.
Or whatever methodology.
Oh, wait, sorry.
Are you sharing it so that you're zooming through it? I'll want to check it out later.
Yes.
How would I go check it out?
The question is where it's all under the flux capacitor stuff. So
okay.
if you kind of remember, one trick with GitHub, and people that know me know that I bring this up every time I speak, is if you're looking for something, so let's say the name of that is SparkML. If you want to look for Airbnb or something, let's say, that's the most unique thing there probably. You can hit T and do Airbnb, and there's the Jupyter notebook right there. And it kind of makes sense. It's under DockerHub. Not a lot, but I've been restructuring and kind of moving things around because before, I had everything under a MyApps directory or something, but yeah. And these Python notebooks render really nicely in GitHub.
Great. Thank you so much.
Yeah, and you can actually export it and so yeah, so here we're actually deploying the PMML, flipping it. Yeah, so I've seen this model, picture you have 2,500 servers out there, and some of them get the updates, some of them don't. You don't really know, and you start building in all this tooling, which ones got it, which ones didn't, tear the ones out that didn't, figure out what's going on. Or, yes, if you're Netflix and you have tons of money, and your stock went up 800% in the last 5 years, what you could do is actually keep that cluster up, spin up another cluster, start with the canary, with that new model. So that would be so that's the immutable. So here I'm deploying both Amazon and Google. Actually pushing out the PMML, flips it in memory, and then any new requests coming in go through that new PMML graph. And here's an example of the evaluation side of it, passing in. What we're trying to do with the Airbnb thing is figure out with the specs of your apartment or your home or whatever, how much money can I get? And these are all the features. Are you a superhost, which I think means something. It's Airbnb, extra people, So now, yeah, so here's the immutable model, right? So this is where you keep, so you basically have one Docker image per model, and that's actually what gets deployed. So think of deploying your machine learning models, right? Like just like you would code, right? Like you're not out there changing code live. Actually, I have a demo of that, but don't do that. But you want to like just push those out, and then keep them separate. That way you can roll back the entire cluster if things go horribly wrong. All right, so let me flip over.
So how do you compare the two models? I mean, there's something that has
Yeah.
to go back. And
Yeah, that's some of the tooling that we're working on. We're actually trying to standardize on TensorBoard, but we're liking the direction that TensorBoard is going, right? And there's a lot more people behind TensorBoard than we thought initially. Like I thought it was just one dude, but they're actually pumping out quite a lot of good things. But yeah, something like that where you could actually see both models rendered, right, like different colors, right, and just make sure that they're within tolerance, right. Some fun things like that. Yeah, also put that side by side with the system metrics as well to make sure the heap isn't blowing out, that kind of thing. All right, so this is where, actually, this is why I was trying to get out of that situation. I can't actually commit the new model, which would then trigger it, but I can simulate the trigger through the webhook interface that the GitHub folks give me. You could actually tell it to redeliver that same post as though I had committed something. So let's get to that in a sec. First, I want to show the load tests. So I'm going to get my favorite thing up here. Oh, and actually, I can't remember if I had mentioned this last time, but I've been noticing for the same price, the Google instance I'm using is the HiMem, it's an N1 HiMem 8, so it's 8 cores, 52 gigs of RAM. In my totally informal, I'm not doing performance benchmarks, and I want to get into that business. I'm actually noticing twice throughput, so basically half the cost as in for the exact same workload and everything. So we might see it here sometimes because of the demo guides, we don't necessarily see it, but it's been pretty consistent. Pretty much everywhere I've demoed, we see it. All right, so let me just explain what's going on here. I've actually got 5. So here's a TensorFlow model. I've got TensorFlow hooked into the Netflix framework, right? This is all the Netflix goodiness where it's emitting metrics like crazy. Yeah, this is going to light up here in a minute, but so I've got TensorFlow serving, and I've got what's the model? It's the minimal model. So it's just literally doing a matrix multiply and it's spitting out. And so we're going to load that up and find out that there's some issues with TensorFlow serving. Surprise, surprise. That they're working on. But so that's this guy here, and actually let me alphabetize it because once this lights up, it's going to get confusing. All right, so that's this bottom right. That's going to be TensorFlow taking live traffic. Here is the PMML. Here's the Airbnb thing that I just talked about. So we can actually flip it in memory and watch it. This is the other data set, the census data set. That's yet another notebook that I have here. Oh God, please don't anyone get on this server. I have to start using localhost or something. Yeah, so the census data set, you pass in your, occupation, all that stuff, and get out. What if you're less than 50,000, you're greater than 50,000. So that's what's happening here. So that PMML has been pushed out. My point here is to show, and yeah, I work with the JPMML guy pretty closely. He's out of Estonia, and he's like Mr. JVM. If he was living here, he probably would have worked for Sun years and years ago, and he just loves all that kind of stuff. So he can spot memory, not leaks, but sort of an inefficient use, creating new objects, unnecessarily things like that.
That was the guy you were trying to have him open source the code, right?
Yeah, Velu, yeah. Yeah, he makes money. It's so funny. He's this dude that like dropped out of his PhD, realized he was sitting on a gold mine, I guess, and so Airbnb uses them. This company HomeAway uses them, which is really similar to Airbnb. That's actually how they found out they were looking to see. I think like Airbnb like blogged about it. It's called open scoring. Is his commercial side of it, but it's basically JPML, and it can do the conversion. It can do all the Spark machine learning models, and we'll convert them to PMML. I've been working with him pretty closely on taking the PMML and then optimizing that, right? Like everyone always complains how crappy PMML is. It's super bloated and it's XML, but with those same techniques, right? You know, the folding of branches, things like that, we can actually make the PMML smaller. And then what we're focusing on for Q1 is to take that PMML and then generate even more native code. So that's the next step. So along those lines would be this code gen thing here. So I actually have a very simple this is pretty cool. So this is, we're actually on the fly. So this is not PMML anymore. This is a JVM running out there, right? It's a Spring Boot app that's running Netflix open source, has all those goodies wired up, using Kubernetes for DNS and for discovery. But you can actually live swap out like Java code. And so I got the idea from like talking to Velu and sort of thinking through the code generation side of things, but then also at the same time, Spark started doing more and more with this code generation stuff, right? Where they take your logical plan and can start to rearrange everything, but then also there's this project called Janino, I mentioned it before, that can take source code. And so, literally this source code gets generated by Spark, not this, but source code gets generated by Spark, gets spit out like this, and then gets compiled on the fly and converted into a Java class. And then that's actually what gets run. It gets cached, right? So that's actually what's running when you're doing queries. For the most part, if you start to inject goofy Python UDFs, then all bets are off, and you should go back to single node development.
And the reason you're doing this is because it's costlier to bring it down and bring it up? Is that the reason?
No. This particular thing, I was talking to some of the OpenAI guys recently. From a rapid development standpoint, this is way faster, right? Even with Docker containers, even with Airflow, I mean, you still have to get up and get a cup of coffee and come back and hope that it comes up, and there's just a lot of steps in there. Also to keep in mind, right, GitHub is not always up, right? So this is something Netflix has dealt with. People that tend to rely on GitHub for their continuous delivery, continuous deployment, you can probably think of a dozen times GitHub's gone down the last couple of years, and it's always the worst time. Netflix runs their own, stash server or something like that. So, but yeah, it was basically, mainly to see if I could do it and what sort of error handling I would have to deal with and things like that. But it's kind of cool. So this is actually the source code. I can change this on the fly. So right now I'm doing equals, but I can change this number. And then here this is the update step. So this is the mutable deployment where I'm actually changing the log running servers. This is the output of it. So this is actually what that project Janino generates. It's got line numbers and everything for debugging purposes. And then, so that's the Velu side. Here's where we do the evaluation. So here I'm checking if it's 21618. No, it's not. It's false. Return is false because it's 21618. Also, do you know that you can render HTML and stuff through Jupyter? The first time I saw this was at Databricks when people were starting to get crazy with embedding everything into the notebook. And I don't know where the Databricks product is now with this kind of thing, but before it was like a subset of HTML. You would deploy it and you would hope that the engineers got around to actually implementing that side of the JavaScript spec or whatnot. It was pretty barbaric. All right, so that's that other service here. That's the equals, and then so now this is kind of cool. This is along the lines of a serverless type of thing. So I'm actually generating code that is using HTTP clients to talk to an internal prediction service. And I thought there's no way that anyone would even think to do this. And I was in Spain, actually. There's this company, BEEVA. Yeah, so that specific project is a big recommendation project, but they work with a lot of banks and things like that. And they have this like legacy prediction server that they just wanted some way to do this, right? They just wanted like a simple HTTP client. So let me find that code real quick. It's basically the same thing as the simple equals, except we're actually importing the famous HTTP client. Totally unsecure. Like you could take down the Trump tax records or whatever. I'm dying to see this. Have they actually come out? Like, do we know how much he made? Yeah, I don't like bringing Trump over around my roommate. She gets physically angry. Starts throwing shit at me. Why did you eat my... Oh, your Thai curry stuff or whatever? That's in the Amazon shopping cart. Amazon Fresh. The not so fresh ones. All right, so... Yeah, here's an example. So we're actually, as part of what you pass in is the URL. So this is actually, this should actually work. Because I think I was getting it to work on the Google right over here. So this is, and then calling predict, we live pass in this user ID, and then like an item ID, and then what's happening is this legacy prediction server, which is actually from my workshop, which is already legacy, that's doing matrix multiply and just returning a value. So let's see if this works. So that's the code that gets generated. Looks a lot like the code that's going to be run. Here it's actually going to update it. So we got the OK there. So here's the evaluation. So this is 21619. That's the user ID. 1006, I think, is like Tom Cruise or something from my workshop. So formerly this was giving a fallback, which is not good. It looks like it's also giving a fallback. Looks like I didn't fix it in Uber, but anyway, that would normally call this legacy server. So yeah, this kind of stuff is actually being used. Kind of cool. All right, so let's load it up, eh? So the naive way here would be to go to JMeter. So let's start with that. And then we're just going to crush it and laugh. But my point here, hopefully my point is made, is that JMeter's a piece of crap. JMeter. We did. Load up all of AWS here. Show us do all of these. So this is going to hit all 5 of those services, or looks like I have the HTTP one. Yeah, save it because it wasn't working earlier. It's going to hit TensorFlow, it's going to hit the 2 code gens, it's going to hit the 2 PMMLs. Load it up. Everything looks good, responses look good. Okay. Yes, HTTP client won't get hit. Oh, am I not hitting TensorFlow? So here, the limiting factor is actually my laptop. But you see some of these times, like, yes, I've actually gotten this down. The last time I demoed this actually in Spain, yeah, I realized the Netflix code I was using, there's basically like a turbo button that you can turn on that I forgot about because it's 5 years later, and I turned it on, and these latencies, they're not usually that good, but they're definitely, you know, 5 milliseconds. So now this is actually evaluating, this is going through all the PMML, right? This is going through the Airbnb PMML. So yeah, we're not going to win any performance contests there. Actually, I think this is the, oh, this one doesn't have, okay, let me change this. This is the one that has. Yeah, Tensor. So actually, this TensorFlow code, I've got this Java wrapper that right now, it's totally not optimized. It's actually using gRPC to talk to TensorFlow server, right? TensorFlow server, which is not the right way to do it. So the like next level, which I'm going to have working, I promise, because I have to have it working for the O'Reilly guys, is going to be that same Java layer, that thin Java layer, so I can hook into the Netflix stuff. It's going to call directly, right? Like using Java CPP, which is sort of a nicer way to do J and I calls down to the C++. And there's specific APIs for TensorFlow. So there's the concept of a tensor. Yeah, so all the various primitives that are involved there. There's a like prediction request, prediction response, things like that.
So is it possible to see the AWS and the GCP side by side? I mean, is that something that's doable?
Yeah, why is this thing? Yep, that's actually, if I had more real estate. Actually, I'll do that with the big load test here. I think that's actually just change one thing here. Yeah, that's right. Okay. Yeah, so let me get them both going right side by side. Let me close out this and get the real load test going. So now I'm using the training cluster to actually, so that like, we're not affecting the prediction side of things, right? So, figure out where I am. Let's do the Airbnb one. Compare those side by side. So the equals one ends up just blowing everything else away, right? Because all it's doing, it's been compiled, it's been like JIT compiled, it's just doing the equals, right? As best as I can, I'm just doing that over and over. So that one barely even registers on the dashboard. And we'll do, so we got the Airbnb, we got the equals, and let's do the, let me just double check the, yeah, that should be right, okay. Let's do the TensorFlow stuff. Which I hope I didn't break. So this should be slamming it. Now, so now look at that, right? We're up to 2,600 requests per second. So here's the Airbnb one. That looks a little weird because 49 milliseconds, that's usually the fastest one. So this is pretty good, right? We're doing 1,300, sometimes it gets up to 1,500 per second, usually around 10 milliseconds. Yeah, I screwed up the TensorFlow one, but Oh, so actually, so in this case, it looks like Amazon is faster. That's interesting. Yeah. So my exciting conclusion that you should go to Google, yeah, just ignore that. So, yeah. So I think that's that. Anything else? Yeah, so next time I'm going to get this thing, I'm going to compare it using gRPC, which is how it's built now, to the native. The other thing too, I want to point this out. If there's one thing that you guys take away from this and get excited about next time, it's going to be the request batching with TensorFlow. And this is something I'm going to focus quite a bit on in the video and the training. So, right, the idea here, and this is particularly useful for GPUs, where you're trying, tell it, so with TensorFlow serving, there's 3 or 4 different parameters you can pass in. You could say wait 5 milliseconds and just get as much, get the biggest matrix you can build, pass that to the GPU. That's one criteria. There's also the size of the matrix, which is something that the TensorFlow code is actually very aware of, very sensitive to. It knows what CUDNN, right, the CUDA code, what that's expecting behind the scenes. So, but yeah, check this out. So, this would be an example of we're combining. This is a matrix times a vector, matrix times a vector. So this could be 2 different requests coming from 2 different people, and we can then combine them in such a way. We add with zeros here, fill the rest with zeros. Make it one big multiply, and then on the way out, we can split that result and send it back. Yes?
So I guess I'm not immediately seeing the benefit of that. Usually the whole reason why you parallelize is because the limits of memory or whatnot. Now in this case you're saying, well, let's just throw even more onto one machine. So isn't it sort of doing the opposite of what you do parallelizing across machines?
Yeah, well, keep in mind that, so you're trading off latency for throughput. And so this is something I actually found when I did have the TensorFlow stuff working. If I was just doing small, through like JMeter, for example, didn't really make much difference. But when I switched over, you just,
Well, I guess I don't mean latency and throughput so much as just you won't be able to do it because, they're not 2x2s. They're like 2 million by, 500.
So the most extreme way to think of it would be with GPUs, right? When you have GPUs on the prediction side, on the inference side, and you basically get one chance to get that matrix over, and the more you can fill that pipe, right?
And then is that figured out on the fly, how much extra space can be filled? Or
exactly, yeah. So they're very wishy-washy in the current TensorFlow serving docs, the whole your mileage may vary kind of thing. But you'll actually see inside of the TensorFlow code where, depending on which GPU, right, because they know which GPU, right, they can detect that. They can sort of, how do I explain? Make suggestions, I guess you would say, or hints at the proper size, right? The number 64 comes up a lot, right? Things like that. It's just that's the empirical.
And then those hints are ones that you have to hard code in for that run, or those are things that can adjust on the fly depending on the data size?
Yeah, that's a good question. Actually, I haven't tried to change it on the fly. I'm trying to remember I was just looking at the code last night. It's a parameter that you actually pass in on the TensorFlow serving start. But if you think of it
I guess I'm just thinking some machine learning, you know how you're defining it, but some of it, let's just, take SVM for instance, you just say, throw it up into a shit ton of hyperplanes and who knows how many.
Yeah.
And, it has to be figuring it out somehow, I presume, and I don't really know how it works under the hood.
But I think if your final objective is to keep all the cores busy, you can always, no matter how big it is, you're batching it, that your end result is to keep the GPU.
No, I get it, but I'm just saying, if you want to standardize a model that will keep working, and the algorithm needs to keep being tweaked every time the data size makes a new model, then it's okay, it worked today, it won't work tomorrow because it's crashing. Not because it's not working, but giving the best number. It's like
And there's a-
crashing.
Yeah, there's a lot of chatter on the GitHub issues about like that very thing is, and yeah, because I'm trying to think, at like Netflix, for example, like we never really did a lot of back of the envelope stuff. Like we just threw it up.
I mean, I've never known for it to screw that up, but I'm just saying I don't know how it works under the hood. But if I now start adjusting it and saying no, do double what you've calculated to do, at that point I imagine it would have issues.
And then check out, so there's the timeout. So that's the actual, well, it's not the best name, but that's the batch window size essentially. This is the number, so I was getting worried by this number, that's why it's super high. The number of batches that are sitting out there. And there's a bug right now in Tensorflow serving where when you hit that limit, instead of sort of pushing back, it just dies. There's something between the Tensorflow serving code and the gRPC library that they're using where it just doesn't recover when it should.
And does it a priori give a guess that that'll happen, or do you find out 4 hours later that
Yeah,
it didn't work?
no, and in fact, what I think is one of the main guys behind Tensorflow serving, because I keep seeing him come up more and more, his whole thing is put it in front of a load balancer and have health checks, and when if it's not performing, then pull it out, because something's wrong, right? Important. But you're more talking about almost deploying different, like versions of these, right? And seeing how they perform next to each other.
I mean, honestly, I'm saying that I don't understand how it works well enough under the hood, but if you're now saying you can double up what it initially thought, and it is somehow magically figuring out how large the tensors can be, and you're saying, yeah, but take that and double it, how do you know that you haven't now, hit a limit?
Yeah, and so not all algorithms benefit from this, but. All right, so I think I've taken up enough time. The way this is gonna work, I should have explained this before. So what are you gonna talk about? You wanna say it? Profiling, Spark, flame graphs, that kind of stuff. So you're coming up next. We got Google guy back there. It's Andrew, but with the D and the R backwards, or the right way maybe you would say. Yeah, I was in Bangalore, and I kept walking past people and going to the right, like I would, here, and they were going to the left, and it was that classic, what's that called now, race, or not race condition, but, so yeah, I think we got it wrong here. I started thinking Celsius too. I got back and I was like, this Fahrenheit stuff's barbaric. I almost switched to Kelvin, I think. Okay, so this is something very dear to me, is flame graphs and Brendan Gray, and you're going to talk about all that, right? Okay. And this is specifically for Spark and for your guys.
I will end up with Spark, but I will start with way more microscopic
Gotcha.
parts.
So I think this is going to be a good talk. That's going to be Kubernetes and Spark. Do you, Lena, want to say something real quick about your startup?
Or if you want me to say that
Please,
then I'm
no,
fine
come on up,
with
come on up. Ladies, come after me. It's supposed to be like that.
Never used it. Have you Okay. Hi everyone. Thank you, Chris, for giving me a few minutes to talk about my project. So I'm the founder of an educational technology startup. We're super early stage. And what we're trying to do is to optimize learning so that each person that want to learn can learn with their abilities possible. We want to use artificial intelligence to do that because what I figured out is that the only way we can really optimize learning is obviously through using massive amounts of data and also creating models that are coming from neurosciences. My expertise is in learning sciences and neurosciences, and so I'm looking for my first AI-focused team member who would join the other partner that I have now, which is focused more on mobile development. So we developed the first app, and this first app is actually currently launching. We have pretty good traction. The sole purpose of this app is to gather data for the models that we're going to build for AI. So we're really looking for the next person to join the team to be able to refine the architecture that we've created and also start working on the neurosciences models that I've been studying. So if it's of any interest for you guys, what we've found so far is that we're going to be using TensorFlow, that's fine here, and also GPU transfer learning. We found a paper that we think should be implemented, but we're not specialists, so we're looking for the feedback that we could get from our AI focusing members. So if it's of any interest, please shoot me emails to Chris and he will forward it to me. Happy to grab coffee with you, happy to answer any questions you have regarding that project. And I look forward to maybe working with one of you guys. Thanks.
Do you have a formal job description and stuff too?
Yeah, sure. I'll definitely send it to you.
Basically, it's like the dream job, right? That's why it's taking the paper and then implementing it, right? And fighting through all the TensorFlow newness and crappiness and all that. So, yeah, dream sort of cross between data scientist, data engineer.
Exactly. So you said it better than me. I'm the CEO. We have someone who's working for on the value. It's really going to be finding the research paper, putting it to production, and seeing it immediately working for students because we already have the user base in the UK, in France, we're launching now in the US, and we did that just the two of us, and we're looking forward to the next step to our product. Thank you.
I've got books. I've got books. Who wants the Learning Spark book? Really does. Who's been to the meetup the most? You really want a book from like 3 years ago? Like, yeah, you already have it. Right. Who doesn't have this? Needs a book in.
Did you also have a newer version?
I don't think this. I don't think they've come out with a new one. This Holden's.
What was the one that you said you really liked?
Oh, this is the best book ever. I have 2 of these. It's the Strata. It's like 4 plot arrows. I think half of them are gone now. It's more like patterns, you know. So, but they use Spark. There's a little bit of data frame stuff.
Hello? Alright.
Yeah.
Oh, that's weird. I did this with my finger and so the speaker's on, right?
Yeah, we can hear you.
Okay, that's weird.
If you turn it to if you put it on the right side, I think we'll be looking at it.
Okay, now I get it. Yeah. Alright. So let's do this. So we ended up talking with Chris online after, I don't know whether we met on Twitter but it was after he had read an article that I had written about very low-level measurements of CPU efficiency and stuff like that, right? And there's some Spark involved, and now I ended up here. So, oh, this is small. So the original. Let's see, where do we have that? So the topic is low-level CPU performance profiling, and I have some examples. And I kind of have a little story about my journey from old school C++ and Unix and Oracle guy towards the new world, right, where you have this JVMs involved in Spark and so on. I still will talk about low-level stuff, but why would you care? I mean, you can always scale out, right? Well, if you're running something on 1,000 nodes, maybe if you spend a day or a few hours with the right tools looking into your data structures and CPU efficiency, maybe you would run your thing only with 500 nodes, right? So, optimization. And I'll show you that, I have some demos as well, and I'll show you the tools that I use, right? Any questions or background? And this may be a kind of a different topic. I don't know, I haven't been at this event before, right? So if it's way too low level, it gets boring. You can kind of start, falling asleep, and I will speak faster. Okay, so I've been doing. My name is Tanel Bodar. I'm actually also from Estonia, the country where this guy Milo was, what Chris mentioned. But I actually live in Dallas, Texas. My history is something like this. I've done Oracle for 20 years, right? And 10 years ago, Oracle database was the best engine for so many things in an enterprise, right? Transactions, it still is very good for that, complex transactions. But people even put emails into Oracle databases 10 years ago, and some even succeeded. Some tried to run, Oracle had a product called IFS, which was a file server where files resided in an Oracle database. That didn't work well, so that's pretty much it. So anyway, so the years have gone by. I mean, Oracle is still pretty much the best engine for ERP systems, but everything else has changed, right? And especially if you come to the Silicon Valley. So I live in Dallas, Texas actually. Okay, and here's my story, 20 years of Unix, Linux, and then 5 years ago I started doing Hadoop, mainly SQL on Hadoop, so Impala and all this stuff. It's very interesting. And I have a Spark performance key with a question mark, so I'm like, don't ask Spark questions for me. If you see code what I've written, it's crap. And actually I'm gonna use a piece of my own code as an example of how to not write Spark. So, but because of the history about there, I mean, I know what to look for, right? I may not know the tools immediately, but I know what to look for when there's a problem. Because after all, is it Spark, is it Tensorflow, is it Oracle, is it Excel? It's just a program running in your machine, burning CPU cycles, and sometimes not burning CPU cycles because it's waiting for something, right? So at the high level, it's all the same. So my contact details, this is the company, we glue enterprise data together, but I'm not going to bore you too much on that. We bridge together this 20-year-old Oracle world with the modern world, so you don't have to rewrite code, right? Okay, so I'm going to talk about microscopic stuff. Couple of things about CPU internals, modern CPU internals. You may already know all this stuff, so you can boo me out if it's boring. And some tools, how to measure actually how busy your CPUs really are. So that's going to be interesting. I'll use an example, an Oracle example as well to show the benefit of columnar data structures, and then I'll look into my Spark journey, including the stupid mistakes that I've made, and how I measured my way out of this problem. Right? Okay, so hopefully it's going to be a fun hacking session. If you run, I'm not running things in a whole cluster, right? Because again, a big cluster is a collection of small machines, right? So I'm going to look into one. So if you're on top, right, I'm actually going to do this as a demo. I may need to tweak my screen a bit. Sorry about this, guys. I will. Okay, this one good. I don't know what my OS X does these things, but okay. Now we have a better resolution. A bit too good resolution. All right. So I happen to have a process running, right? This is okay. You know, again, at this microscopic level, it doesn't even matter what process it is, right? So this process, it looks like it's 100% on CPU, right? So leaving the OS scheduler things around, the process is migrating. So would you agree with me that this CPU is now 100% busy? So, and this is where I should have put a Morpheus picture from Matrix. Like, what if I told you that your CPU might actually not be busy? Right? So this operating system tool says 99%, but let's run a command. Actually, I have a tool, I'll show you how to run it. So let's run a command. It's this process, which is 100% on CPU, so to speak. But I will run a different command. It's a Linux command called perf, which can peek inside CPUs. Because CPUs, all modern CPUs, have performance counters, which tell what stuff happened inside the CPU. So I'm not going to just run it. I'll run it for a few seconds. It samples the CPU performance counters, or it enables them and samples them. And when I run Ctrl-C, it will just show me a report. Right? So I did not go and ask Linux, what do you think the CPU utilization is? I did not go and ask Linux scheduler metrics. I actually went and enabled some counters inside the physical CPU core, and now I report it. Right? So I apparently kept my, I kept this tool running for about 10 seconds. Actually, you see, total elapsed time, like wall clock time was 10 seconds until I hit Ctrl+C. And I burned about 10,000 milliseconds of CPU as far as the operating system sees, right? So these two guys come from the operating system. Actually, all these four guys actually come from the OS, scheduler, and virtual memory management. But the metrics under it come from inside the CPU, right? So during this 10 seconds, the CPU physical clock generator generated 29 billion cycles, right? So therefore, it looks like I have a 2.8 gigahertz CPU. 10 seconds, that many CPU cycles, right? During this 29 billion CPU cycles, we managed to only execute 20 billion instructions. So my CPU did all this work, burned all this energy, but somehow it ran less instructions than there were CPU cycles, right? So, and we can actually calculate IPC, so how many instructions per cycle we did. We managed to do only about 0.7 instructions per CPU cycle on average. So that's one indication that my CPU core actually wasn't that busy, okay, despite the Linux things. And what's going on? Well, stalling is the keyword, right? When a CPU can work and run instructions on memory locations which are in cache and so on, it's all nice, it runs these instructions. But sometimes it cannot work because the memory address, what it's working on, is not in cache yet. It's not loaded into a register, right? And that's when the CPU stalled, but it's not like the CPU turns itself off. The cycles are still generated. The CPU still burns empty cycles. When you run, so this is what stalling means, and there are many reasons for stalling. So sometimes the pipeline cannot just go ahead and actually do the work. So, and the thing is that when you run pop on Linux, Linux just says that, hey, as far as the scheduler is concerned, I'm on CPU, right? Therefore, I must be doing some work. But inside the CPU, you're actually wasting cycles waiting for something to happen. And this something is that memory line needs to arrive, or sometimes there is some conflict and so on. Okay? But this tool allows you to measure it. And there's more stuff like branches, if you have frequent loops or branches, and CPUs have branch predictors. If there was a mispredict, you will see a branch miss and so on. And there you even see how many memory, level 1 data cache accesses you have. And on this CPU, for some reason I don't see the lower level cache, level 3 cache levels. But basically what I'm showing you here is two things. It is possible to peek inside CPUs and see how efficient the CPU cores are. And the second thing is that there is no one-to-one relationship between a CPU cycle and an instruction, right? And the third thing is that when you run top on Linux, top still means that I'm 100% on CPU, while these numbers here, the front end and back end, I'll explain what these are. You see the CPU core, or part of this, the beginning part of the pipeline, or what comes before the pipeline, it was 68% idle. And the back end, which actually does your operations, arithmetic operations, it was 58% idle. Okay. So, okay, so here's the command, and here's an example from some other test I ran on another CPU. I even see things like how many memory accesses you have. So this is lower level or longest latency cache, and when you have this kind of cache miss, then it means that they actually have to go to memory. They have to go to RAM 200 million times to get some memory lines to work on. Okay, so that's kind of the intro. And by the way, I have a blog entry where I explain all these metrics as well, so you can read more. Okay, so if that doesn't make sense, maybe I should show this. So I stole it from Intel website, right? A modern CPU, looks like this. You see, it actually has you have a single CPU core, but within the CPU core, you see you have multiple execution units. This is one execution unit which can do these kinds of operations, like multiply. Then you have another execution unit which can do adds and then whatever. This can do jumps, and then you have the memory load store units and so on. So basically, this CPU can actually run, maybe up to 6 operations per cycle, right? Some memory loads and some actual calculation, right? So that's why. So basically, where I'm getting at is that if you don't have bottlenecks like random access, then you might actually execute more than one instruction per cycle. Right? I showed you a case where we executed less than one instruction per cycle because we were waiting for something. But you can actually, thanks to having a super scalar out of order processing, you can have more than one instruction per cycle. Okay?
All this is just one core, right? And if there are multiple cores, then you...
Yeah, and this is just one core, right? So if you have 8 cores, then you will have to have this times 8, right? But the only thing that level 3 cache is sometimes shared, or is often shared, but the other caches are per every core, right? So within the single CPU core, you have concurrent execution. Sometimes it's even out of order, right? If there are no data dependencies and so on. And modern compilers know about this stuff, that when they compile optimized code, they will, deal with dependencies if possible. Okay. Anyway, so the keyword is pipeline stall. For example, if your underlying data structure, like your scanning, for example, or accessing, is so inefficient, so sparse, you're going to be waiting for memory access a lot. Okay. I'm sure you've seen things like that before. So the CPUs are very fast, right? So if you have a 3 gigahertz CPU, then the register access is some nanoseconds, but it's less than a nanosecond, like 1/3 of a nanosecond. If my math is correct, it's late. But memory access, if what you want is not in some level 1 or level 2 or 3 hash, then the main memory access, it's already like 200x slower than your CPU cache, your level 1 cache. So RAM is slow. Actually, one of the reasons for this talk, or why I started looking into this, is that there are so many systems or people who say, hey, we have an in-memory system. Our system, our engine is so fast because everything is cached in memory. Well, if you just take your own disk data structure and cache it in memory, then you're not going to get the most out of your CPUs. So anyway, so the takeaway from this part is that CPUs are very fast. RAM is very, very slow, hundreds of times slower. So better not access it as much as, better optimize it. And the caches are somewhere between. Okay, and actually Jim Gray, from Microsoft, and a very big contributor to this world, has said, hey, this is dead, flash is this, and RAM locality is king. That's where I want to go with this talk, is that let's look into the underlying data structures, and then we'll end up with seeing how it looks like in Spark. So if you just cache your data in RAM, you don't have a proper modern in-memory efficient system yet. Okay. So and usually the answer for analytic apps is columnar data structures, right? So the problem with the old school data structures, if you take a transactional database like Oracle or something, is this. Everything is organized in rows, right? So this is one row, this is another row here, third row, and so on. And now if you want to, let's say, sum up one column, well, it looks like, hey, it's just all, one column. But actually, well, the data is very sparse. You may end up having to follow some sort of a pointer to where this column is, right? And then you read this column. And you may, and then you have to jump here and read the next column and so on. The data is very sparse, and RAM is very slow, right? If you have learned that RAM is fast, that was true like 10 years ago when everybody was waiting for spinning disks, right? But now even Flash is fast and so on. So RAM is actually slow compared to the CPU cache, right? So that's one problem. And another problem is that this is like an idealistic picture. That in real life, if you have a row row major data structure like that, then this column you want to sum up, it's not always in the same place because you have variable length columns before that, right? So then there's one more thing worth knowing is that if you want to read 1 bit or 1 byte from memory, then the memory controller is not going to read 1 byte only. It will read 64 bytes, right? Because that's what the cache memory line size is on a modern Intel machine, right? So if you read 64 bytes only, if you actually consume 2 bytes from there, then there's a lot of throughput to waste, right? And that's why, and by the way, if this little memory structure you want to read is in the middle, on the boundary of these 2 memory lines, then you end up reading twice as much, right? And now the high level or conceptual overview is really this. With a columnar structure, you actually take, you take a million records, and then you take the first column of the million records and you just store all the values next to each other. Then you take the next column of this million record batch and you store it in the next area. And that's when you wanna actually do some sort of a sum. You have much better data locality. Even if you have to read 64 bytes, well, you're going to read multiple values for many records, right? So there's much less data to scan, or sometimes you can filter the data first, and if there is nothing in this data set which matches your filter, then you don't even have to go and project or read the other columns at all, because there's nothing matches in them, right? So this gives you much better locality, and by the way, better compression as well if you want to compress this stuff, because you have potentially duplicated values here, just next to each other, or some sort of timestamps where the beginning of the timestamp is pretty much the same, but only the last microsecond or millisecond changes. It's possible to do like bit level compression for these things as well.
But most common OLAP databases, when you store it as in columnar storage, it becomes append only, where you can't really modify or update the rows.
Yep.
So what is the solution for that?
Yeah, so the question is that for most, when you talk about most columnar databases, which are columnar like that, often or usually they become sort of append only. You can just only add more data, but you cannot go and modify individual items in the middle because it's hard and complex. If you want to modify one item here, will you decompress the whole column or the whole chunk and put it back? So some databases don't support modifications at all, but some actually do, and they have Oracle happens to do that. They have a base. You load a lot of data, and when you modify something, it doesn't actually modify that column. It will add a new version of that row in some in-memory store, right? And later on, maybe it will compact it. So every time it scans the column, it will check that, okay, I'm going to take this value unless there is a newer value in this delta store. And Cloudera's Kudu works like that as well.
Which one?
Cloudera has an engine called Kudu, which is a like HDFS is a file system, and you put Parquet files in there. But Kudu is something like much lower level. You can just put rows in there and get them back. It's like a database storage. Okay, I want to get to the Spark part as well. So I do have some demos, and I have links in the end where we talk about. I have links in the end to all the tools that I'm using, and also the source code, my crappy source code what I've written. So I have a. I think I'm not even going to show you the C code here for this microscopic demo. I'm just going to run it. If I find where was it? Okay, so I wrote, just to continue this microscopic example, I wrote a little C++ program which I'm going to generate, first I will generate an in-memory array, 10 million rows, and I will have 1,000 columns. And it's a very simple example. It's like this thing, right? Actually, it's actually like this. like this guy, right? I have 10 million rows and 1,000 columns, and each column is 4 bytes. It's a very, very kind of rigid array, right? So it's, I don't know, some gigabytes in size. So, so it will generate this X gigabytes of data, and now I will count only one column. I have 1,000 columns, very sparse data, and I want to count only one column out of this, right? So I think it should be done in a moment. Okay. So, and on this side, I will actually run the perf command again, which tells me all I want to know about the memory and CPU usage, cache efficiency. So I will say run this guy, and now I will say count this one column. Okay, it counted it very fast. Okay, so it took 200 milliseconds to count 10 million values. And sorry, I wasn't even counting them, I was summing up whatever values were in. Right, so I was doing a very columnar scan out of a very big and sparse structure. Right, so and we ran 70 billion instructions, and you see it took 500 million cycles to run 70 billion instructions. So on average, a single instruction, on average it took like, you know, we only could run 0.12 instructions per CPU cycle. We were stalled, waiting, doing nothing, waiting for memory to arrive for 7, 8, like almost 8 cycles per instruction. And you see the CPU backend and front end were 90% idle. I had a slide, I forgot about the backend and front end. CPU backend is where you actually execute the instructions, but front end is what fetches the next instruction, decodes the x86 instruction into the RISC microarcs that the Intel CPU nowadays is, and so on. So, but anyway, both of them are mostly idle because they were waiting for RAM, because I was doing such random access on this very sparse data structure. I did not get cache locality. For every memory line I read, I only got like some 4 bytes what I actually wanted to sum. Okay, and now I will run the same thing. I will generate this once more, but it's 10 million rows, and I'm going to generate only one column, right? Because if I had a columnar system, then I would, if I want to count this one column, then it's in one place, or in a few places. I don't have to go through a sparse structure. So, it generated 10 million records. I will count all of them. You see that the number is the same, or the sum. I didn't count, I summed them. The sum is the same. And now, let's see. Instead of 200 milliseconds, we did the same work in 10 milliseconds, 20 times faster. Because now we only do, because all I wanted to do is I wanted to sum together one column only anyway, right? So now I just went through this one column, and it was nice and sequential, right? So this is a very silly example. So it's a very low level and silly example. So I didn't even have the other columns here because I didn't want to count them anyway. But let's see, we are roughly running the same amount of instructions. You see 70 million instructions, 69 million instructions, right? But in this case, you see, it took 28 million cycles to run it all. It actually took 3 times less CPU cycles than instructions. So on average, we managed to run, you see, 2.5 x86 instructions for this counting per CPU cycle. So this is now the other extreme where a single CPU cycle can do many things at every cycle. Okay, and we didn't stall much at all. Okay, and I could now go deeper. You see, unfortunately I don't have the memory line on this CPU. So some CPUs you can actually report the memory access. Probably in this one as well with some tweaking. So I'm not able to show that we actually access less memory. But there are counters which tell you how many times you went to RAM to fetch a 64-byte line. Okay. So anyway, so this is the beauty of columnar approach.
Yes, I did something like this. I think it was last year, showing the matrix multiply, and if you go row-wise times column-wise,
yeah. If you matrix multiply, you wanna you wanna iterate through 10,000 values, 10,000 records of the same column, then you might want to do this by column, right? I'm not sure how much sense I make right now. It's late for me. Okay. So columnar data structures are awesome because you get the locality, and all the data you want for this specific task is close to each other, and you don't have to go to this other memory location unless you want to read something from them. Okay, and you maybe heard about, or probably heard about SIMD, especially when you do GPU stuff, right? So SIMD is basically something where you can actually run even more complex instructions. That you don't actually run an instruction on one memory location and do something with it, but you actually have a single instruction, and this instruction can operate on 8 or 16 adjacent memory locations at the same time, right? And that gives the CPU, remember the CPU diagram, CPU has many execution units. If you do this, it's like a batch instruction, right? If you do this, then the CPU has more opportunity to optimize, so that how do you keep all the execution units busy and actually get what you're paying for, right? So basically do the same work with less instructions, but those instructions in themselves are more complex internally, right? Because they operate on many data elements, right? You get more concurrency inside the CPU. However, it's beneficial only if the underlying data structures allow it. SIMD is pretty much not possible on this random sparse data structures. You have to have columnar, because that's how you can run, you pass like this beginning address here to the SIMD instruction, and it will just, all these adjacent locations are inputs for this operation to do, right? And actually for that reason, I also have another command called experiment AVX.
There's a question.
Yes?
Yeah, so you mentioned a couple of times that the data structure is sparse. It's not really that it's sparse, it's that the part you care about is sparse, right?
Yes.
Okay.
Yeah. You're right. Yeah. So it's a very great point. So the data structure itself is not sparse, because you fill up all the memory you have, right? So you have something useful there.
It's just you're skipping a bunch of it when
Yeah.
you're doing all your calculations.
Yeah.
Gotcha.
Exactly. So you need to organize your data structures based on how you iterate through them, right? And what's most important, right? And that's where often being a database guy, that if you filter by these columns first, then that this should be columnar, right? So because that's what you land. Maybe you scan through 1 billion records and you filter, and you only get 1 million back and do something with it, right? So 999, so the biggest hit will be where you filter. Okay, so it's the same thing, but we compiled it with a special option, or actually we changed the code a bit as well. So I will do the same thing. So what is it, 10 million records. I will generate one column. And now, so basically it's the same thing what I did previously. And I now have two options. I will iterate through it using the old school simple instructions, and then the next time I run it, I will iterate through it with SIMD parallel instructions, right? So let me run this guy. That was really quick. So previously, the previous demo was 9-10 milliseconds, right? So that's the same thing, right? Because it's not, the binary is compiled with this stuff, but I'm using a function which is not this magical SIMD one. So anyway, but this is what I want to demo. So now I'm doing the same task with the SIMD instructions. And you see it went even more efficient. So instead of 10 milliseconds, it ran in 7.4 milliseconds. That's like 25%, right? Or 33%, depending on which end to look at. But that's now gets pretty crazy. You see, it's 7 milliseconds. I think this must be a mistake here. So that opens a whole kind of forms how the performance events happen in the CPU. They are not, the CPU doesn't report them back every microsecond or something. So you may actually have to run a bit longer test to show the cycles part. But let me, 10 milliseconds, 28 million cycles. I think my test was maybe too short. Let me try it once more. Non-vectorized. If you have these fluctuations in these numbers, I mean, I guess the advice would be that if you profile this thing, run your loop that will run for a couple of seconds, right? Not something which runs for 500 microseconds, because then you have this measurement, granularity, irregularity, right? Anyway, so this looks better. So if you don't like the output of your experiment, run it again until you see good numbers. So the thing is that, okay, now it still runs in 7.5 milliseconds. Oh crap, so there's something wrong going on here as well. So, but we used to run, let me see the previous example. So this was the bad one. See, so this was the previous binary. It was 70 million instructions, and we ran more than 2 instructions per cycle. These were the simple instructions, okay? 10 milliseconds, 70 million. This guy is 7 milliseconds, but suddenly we dropped from 70 million to 7. We ran 10 times less instructions, right? Nevertheless, we were faster, right? I mean, we were a bit faster, we ran much less instructions, because these are now the complex instructions, right? So we might run them much less. I guess we gotta trust this guy. But yeah, so how many? So that's a core metric. How many instructions you get done, and how many cycles you used for that. How much did you store, right? But this kind of shows you that all these microscopic metrics you're looking at, you need to put them into the context of how much work got done, right? Because if you have some manager who looks into just some sort of efficiency, this guy was so idle, use something else, Maybe you get your work done quite slower, but the number goes up. So, you shouldn't do that. So you should always actually put these things into the context. How many orders you process, how many models, how many scorings you do, and then so. Yes?
We did something like that. I'm in the industrial robotics industry, and I'm a project manager for a large automotive maker. I can't be too specific, but we basically translated one abstract robot language into another one, like a parser. And at some point, the runtime of this translator was up to like 15 or 20 minutes, because it would run through all these tables. They were large, and they looked for specific variables over and over again, like a couple million times, as you have suggested also in your applications. And then we did some TikTok analysis where we would spend most of the runtime and boiled it down to the columns and the variables that were relevant in that process. And eventually we brought it back to like 1.5 minutes from 15. So a factor of improvement of 10, and from there we took from there and kept on improving, finding bugs, and making it happen. My own customers were happy.
Yeah. So data locality matters, because the CPUs are very fast, but RAM is multiple 100 times slower, right? And again, I have some stories from my Oracle performance guy days. Like 20 years ago, when you had a sorting algorithm, the sorting algorithm, what our algorithms in the database were naive. They just thought that, hey, I have that many rows, I'm going to optimize it, that I wouldn't have to do too much I/O to this and spill to this, right? But then at some point of time, when CPU caches became big and relevant, right? Then new algorithms, optimized algorithms showed up. Like, hey, maybe I don't want to optimize for this. Maybe I will just do smaller batches at a time. I will run more instructions. I will do more. The complexity is bigger. I will run more instructions. But most of the instructions run out of cache. So I only sort maybe 2 megabytes of data at a time, do it in the cache, send it up, right? Next 2 and so on, merge later, right? As opposed to trying to sort everything which doesn't make fit in cache. So that opens up interesting possibilities for cost-based optimizers and stuff like that. Okay, so I should probably stop this here. So this is, I have the source code in GitHub. The database example, I'm just going to fly through it. So it's a similar thing that I did that happens to be with Oracle. I only had a tiny 8 gigabyte table. I cached it entirely in the database memory in the traditional block format. And it's worth maybe as a summary. So the last option is I ran the same query in different modes, and I cached everything in the database buffer cache. Right? You have blocks in disk, and you cache this in the buffer cache, like the old school databases do. Or I enabled a special option called, this is an extra cost option of course, I enabled a special option which is an in-memory columnar format. So Oracle takes its data, it's the same on disk, but it transforms it into columnar and in a separate memory location. So the same query, same data, stored in a different format. No disk I/O, so this is a disk I/O. But the proper columnar format gave me 50x better bang for the buck. Right? And here's the example again if you deal with the old school databases. So old school databases are optimized for OLTP, right? That's the burden, you have to carry to the data warehousing and the analytics world. And these data is organized in blocks of 8 kilobytes usually, right? So it's very, you can change it as well. And the data is in this kind of, you may need to modify some rows, and the rows grow and shrink and so on, and you have to then, this block structure needs to be able to handle all this, all these changes. And now inside the row, for example, how Oracle works, is that if you have a table with 4 columns, well, you have some bytes in the beginning, and then you have a length byte for the first column, and the length byte for the next column, and so on. So if you want to go to column number 4, you have to jump from here to here, add plus, 7, and now jump here, and you know that the next column's length is here. So there's a lot of pointer following essentially going on, or offset following, at fairly random locations in memory as well. So, and then imagine if you have a data warehouse where you have a fact table with 500 columns in this format. You're just going to waste so much CPU. And again, the visual illustration is this, that if you normally, in the old school format, you have a row major stuff, data storage. You have a first row here, column 1, 2, next row, column 1, 2. You see, it's very sparse if you only want to sum up column number 1. If you want to insert or update or delete a lot of rows, then it's not sparse, because if you want to delete the row, you want to delete the entire row, right? Or if you want to insert the row, you just want to put it into one place. But if you want to do analytics on it, then it's more sparse. And columnar, format will just do this. But let's take 10,000 rows, and for these, let's take the first column from all 10,000, put them here. And now let's take the column 2, and so on. So, and then you just have this transposed, potentially compressed chunk of 10,000 rows in a different format. And then you go to the next 10,000 rows when you are, inserting. Anyway, so, and I will spare you the details, but I did some math even that how many instructions per filtering and counting Oracle did, and the best case I counted 69 million rows, and I got 43 instructions per row. I scanned, filtered, counted. And this actually Oracle cheated here, because when they build this in-memory structure, they keep min and max values for every chunk. They take 10,000 rows, do their transposing, and then they keep min and max value for every row, right? So if you do a max, select max, then they can just go to the chunk headers and read it from there. So all kinds of interesting stuff going. I will upload the slides as well, or I'll send an email to Chris. I'll skip these parts, because there was some promise of Spark as well. Okay.
Yes, I think we have until 9:30. So.
But it's going to be hard stuff. Somebody's going to be machine gun.
Hard stuff.
All right. Okay. So any questions about the previous stuff? Yes.
So two quick things. One is a lot of times you'll try and read in, say you want a column, but when certain values of another column are greater than such and such. Column nor row, neither one will really help you much in that case, right? Like let's say you want to know all of the incomes of the people who are, over 40 or something like that. And so people's age is one column, or income is another.
It's cool because if you do it like this, if you have a billion records in this column format, then and it's organized into chunks of 10,000 records each, then when you scan it, you can give me all people who are over 40 and give me their salary. So let's say this is the age column, and this guy next here, this is the salary or something like that. Well, if you scan through the first chunk and you don't find anybody who's over 40, then you don't have to go to this chunk and decompress it and do anything. So there's a bit of a win there, right? And then you go to the next chunk, and if you find there's at least one person who's over 40, then you have to go to this chunk, decompress it or whatever, and go to that index and find the salary, right?
And then the other question was, you were talking a lot about basically the memory is slow, but what you really mean is the non-cache memory.
Yes.
And so when the cache is reading in, it's 32 or 64 bits, bytes, whatever it has. You'll have captured several of whatever the things in the column you might want. Does the CPU automatically know I don't need to hit memory again to get the next one because it's already sitting in cache? Like, does that automatically happen?
So it's the CPU is smart enough that if you happen to have a cache line already in cache in some level, because somebody else read it like 2 microseconds ago, right? Then if the next process or trail or loop iteration wants to access it, it comes from cache immediately. Yeah. And CPUs are smart; they do prefetching now. So the most simple is if you do scanning, right? Then CPU, the memory management unit, can do prefetching, right? So while your burning cycle is doing something, we are loading more rows. And even if you do array iteration, right, we'll see that, hey, there's a pattern here that we're reading from a location number 100, and then 200, 300. Well, it looks like we are iterating through some array slots, right?
So let me correct it, not the CPU that does it, it's the database that actually does that. It records to the pattern and then it...
No, so this is different level. Database issues IOs to the operating system, and that's the disk IO prefetching. But CPUs and the memory management units inside the CPU actually do it at the memory level as well. And then you have compilers where, if a compiler is smart enough, it can generate hints. There are like instructions, like, hey, even though I'm doing this work, I want to submit an asynchronous read request for this location. And a couple of months ago, I read the first announcement that there are the first Samsung or somebody.
How does the compiler do that? We can take it offline. But I've worked in this area for a long time.
Yeah.
You haven't talked about TLB, you haven't talked about buffer cache, you haven't talked about timestamps, which actually take a long time processing instructions.
Yeah.
We haven't talked about how much you have just naively assumed you can just add to registers. That is not what it takes. Most of the time, the things that actually spend time doing timestamp manipulation.
Yeah,
So
but the timestamp has changed.
More than what you have talked about.
Timestamp has changed because timestamp used to be a system call which went to not to CPU, it went to some sort of a
No, I'm not talking
generator.
about that. I'm talking about the database timestamp.
Are you
Which has different formats with it. There are about 64 different types of timestamps. And to convert them from 2 different timestamps, that takes the longest time. That's about 100 or 120 instructions.
Data type conversion.
Optimize those. That's why I know that what I'm talking about.
I haven't even disputed it. So this is why I started from saying that this is super microscopic, right? I wanted to talk about CPU and cache of how programs run. So, my first demo was a C loop, right? So there are so many layers because you can go up and you can go all the way to the optimizer, right? Sometimes your query is slow because the optimizer does something wrong. Okay, so let's see. Let me do the Spark thing as well, so I will break that promise. If you guys invite me back, then maybe someday we can go one level higher. Okay, so Spark example. So as I said, I'm not a Spark expert. I'm still kind of getting started. But first thing what I did was to find tools to investigate Spark. Because if I write a Spark job and it's slow, I mean, what shall I do? So I usually start find tools first which allow me to troubleshoot and investigate this thing, right? So what I'm going to use here is perf, profiler, and flame graphs, and I have URLs or links to the GitHub pages and the authors as well. So Databricks and Spark developers realized the same thing, that if you do scanning and analytics and these batch operations, then there are so many repetitive tasks. You're doing a billion loop iterations just to scan and find data. So it's the same little loop that you run it a billion times, right? And if at every iteration you have to follow a bunch of pointers and do a lot of if then else logic, that's how we have too many branches. That's how we just burn too many CPU cycles. So that's why Spark guys built this tungsten data structure, so that instead of using some sort of JVM objects, which are very flexible and safe, but there's a lot of overhead. Instead of that, they bypass JVM's object allocator, and they're just using, hey, just give me some memory, give me a contiguous range of memory. I'm going to manage stuff in. So there's no garbage collection. Well, there is no garbage collection by JVM, but you have to manage what you do with your data, right? So somebody has to do the job. But at least you can control it and do it your way, what's suitable for the task at hand. So, and anyway, so now we have something called unsafe row in Tungsten, which I'm not going to go into details, but it's much denser and more co-located than this, where every single record was this array plus pointers to some string and int and so on. So it's much more dense. And similarly, when you actually now want to scan through millions of these, then this array structure or this table structure is much denser as well. And basically, it's as I understand, it's column, right? And that's what I want to show. Okay. So that's also if you Google, you'll find articles how they do this stuff, and they have awesome results. And that led me to now test data frames, right? RDBs and data frames. So, and the silly test that I did, again, it's in the GitHub as well. I just took the CSV file. I think it's like 40 columns, comma separated, and it has 1 million records. It's like 300 megabytes. So, and basically, I wanted to make this. I just wanted to count one column values from the CSV, right? But before, I parsed the CSV and then actually made it into an RDB. And again, you will spot something very obvious very soon if you have done Spark. I didn't even run it in parallel because I wanted to understand from the lowest building block. So before I go to parallel and scale out and all this complex shuffling and stuff, I want to understand this small thing. So I parsed the CSV to the RDB, and then I will also do a repartition one, because I didn't know how to parse it directly into a single partition RDB. I just wanted to make it as simple as possible, that I would only have one task, one partition process, right? So I issued repartition, and then I also said cache. So, because Spark is lazy, unless you actually use this data, unless you actually reference this data, it doesn't bother doing the parsing here, right? That's where the Spark's lineage and this pipelining comes in, right? It only actually goes and does this work when you try to use something down the line, right? So, so basically this is the CSV repartition, and also what I did is I issued the data.cache, so that's the RDB.cache, and also I ran just some sort of a max command on this column of inference, because I actually I had to touch the values, and I had to use them in order for this to dig in. So, okay. And then I will essentially do this as well as I could, right? So I took the RDB and I wanted to sum up one column. And by the way, the data came from CSV. The data came from CSV, but this particular column I wanted to sum up. I made it into an int. It was the year number, like 2008 and stuff like that, right? So all I wanted to test is if I iterate through 1 million elements, how fast can I sum them, right? And this guy took this is now not the CPU time, that's the elapsed time, 0.3 seconds. Okay, well, good enough. So cached RDD, 1 million records. I counted 1 column out of 40 columns, 0.3 seconds. And we don't have time for running the CPU numbers, but we will do that as well and see similar stuff. So, okay, so that's RDD. But data frames are these awesome things which solve all the problems in the world, right? So it's going to be much faster. So I did the same setup for data frames. It's the same CSV to an RDD, and then I converted it to a data frame and I cached it. So you see, that's the extra stuff. I created a data frame, I defined the schema number, and I cached it. And also I calculated the max of this column of interest, just to kind of materialize it. Okay? And then I ran the same command. Does anybody see anything wrong already? That's why I say it's a silly example. It took 4 seconds. Data frames are supposed to be faster and better than RDDs. This took like 10 or 12 times more than RDD. And you know, this doesn't make sense. I mean, either there's a bug somewhere or I'm stupid, and of course I was stupid. So it's not enough to have this better data structure, like columnar or whatever, if your code actually doesn't take advantage of it. Because what I did here is I iterated through. So basically, I went through this RDD and I used the old way, very old way of doing things. I iterated through every element in this data frame that RDD, and I took, I had like a billion records. A million times I went there, took one value, and summed it up, or added it together. And then I went back one more value, and so on. So I didn't push down the summing to where the data was. I actually pulled all the data or copied it into some location, and then I did the plus operation. So I was using data frames wrong. What I should have done is use data frames as they're supposed to be aggregated. So I would just say data frame, aggregate, and sum up here. And this uses now the Smart SQL and the Catalyst logic to actually understand what should it do. And that pushed down the summing to that column of data. So we only iterate through the column, I summed it up, and then I returned one sum. Right? I returned one sum once as opposed to returning 1 billion records individually and summing them up at the top level. So now it's 0.001 seconds, so it's 8 times faster than the RDD, and it's about 100 times faster than my silly incorrect example. Right? And that's an example that it's not a right. Even though I started from the CPU monitoring and perf and stuff like that, you should not really start. You shouldn't dive into the CPU level and see what your pipeline efficiency is. You should actually go and see what your code is doing. Right? Are you using this method thing the right way? And that's why I used these flame graphs by Brendan Gray. So the profiler that I used, the honest profiler, can generate output for this tool, and these flame graphs. Actually, let me see which one. This is RDD. They will tell you where most of the time was spent, right? So I'm not sure if you see that. So this is not the order of activities. This is, if this thing ran for half a second, then the widest part is that, out of half a second, maybe 300 milliseconds were spent in this wide area, right? So this kind of looks, and you can start walking downwards or upwards to see what methods take most of the time. So there are some issues here. So this mostly shows this Java classes. It doesn't show all your Scala, this anonymous functions. So, but the point is that at least now you know where to look. So you should kind of understand what these methods are doing, as opposed to trying to figure out what the heck this is. Because this is not very wide. It doesn't take too much time, right? So flame graphs to the rescue here. And so I think I'll even stop here. So that's just the illustration that,
What was the intuition though there? That super long bar was what, like integer up or something?
Yeah, so
That was the crappy version of the code?
yeah, so actually the intuition actually was the first intuition was that hey, this cannot be so bad.
Right.
I'm doing something wrong, right? So let's say this is the crappy version. So this is the crappy version, and this is the final. Right?
Good stuff, right.
And I went to the crappy version, and unfortunately, this is not the best example. Actually, the Luca Canales, the other guy from CERN, he had a better, example. But what so nothing, unfortunately, here points out that, I'm doing something wrong. But what I did see is, what I did know is that what I want to do is I want to go through one column of integers. It was one column in a columnar format, and it was just integers, right? So, and then when I start looking into this, so the widest area, so this, we start from the bottom, this is the main beginning, where we call initialize our workers, whatever, and there is some reduce, some for each, you see there is some sort of iterator, right? Who's code again, so this is,
Yeah, that's where it's taking that logical plan and fusing everything together. Yeah,
Yep.
so maps and filters and things that can be fused.
Yep. Yep.
But so this is probably what, Spark 2.0?
Yeah, this is 2.0.2.1, and basically, so this is, well, it looks like this is where the iteration is happening. We have the for each here, so it's, and now we have the data frame access logic here. But what kind of, and you see the catalyst is here somewhere, right? So again, we are using Spark SQL, even though we are not running SQL against the database. It's Spark SQL's relational logic against data frames and data sets, right? But what was very interesting for me, I saw like some string coding and decode and stuff, UDF8, whatever it is. And even though there is, I unfortunately cannot provide you a completely clear direct link here. What I knew was that I wanted to sum up 1 million integers. And now I see some UTF-8, whatever, encoding. So it's like, so that made me think that, hey, maybe we're like accessing some other data as well. Because I knew I had a lot of string columns in this data structure as well. So there was like, hey, maybe, it's I don't know, accessing the entire objects from this data frame. So unfortunately, there's a bit of guesswork. I don't like guessing, right? But as I conveniently run out of time, then this may be for the next time. So I hope I showed that it's possible to measure many things, right? At a higher level, you profile your methods like a developer does, and you can go much lower as well, right? And the perf tool, you can actually use it for on C++ as well, or C, right? So like Oracle is C, right? So I run perf and I see Oracle functions showing up there. Yeah, I think that's pretty much it. So my contact details, I'll send you the slides and you're gonna just send.
Yeah, I think that's how you and I got connected, right? Is that you?
Yep, that's exactly it.
That was your blog post.
Yeah.
Yes, keep an eye on like your blog, obviously, but then Brendan Gregg also. There's a bunch of N's and G's in there, but yeah, Brendan Gregg. He was at Joyent and is now at like Netflix, and yeah, doing a lot with.
He's the guy who invented flame graphs.
Totally. All right, we have like 35 minutes.
There's a Coursera course on Scala. It's like the level 3 course, which goes into distributed programming, and they talk about how to run it across massive multi-CPUs, and it's a pretty intense course, but it's very useful to start thinking in that terms.
Yeah.
That they show how you actually create buffers, and without any locking, you pull it back again.
Yeah.
So that's like similar what Go is doing, but this is way cleaner.
Yeah, because actually where I didn't even get to is, I showed you the most microscopic low-level stuff, and then I went profiling Java methods out of this code. But really, if you're a developer and something, you should actually check your structure of your data flow, right? So, and then, but I didn't see a change actually, so that's why I went one level lower.
Interesting. Yeah.
But I'm still kind of a beginner here. Well, okay, so I'm gonna.
Yeah, these are really hard to read. Yeah, real quick, my roommate is here from Techstars. Techstars is, yeah, you want to say something about Techstars? Like, kind of an incubator, not really? I still don't understand. current office is our house, right? Because you guys got booted from the.
We're transitioning out of our office space in Sonoma, so there's a small team in San Francisco, and largely headquartered in Boulder, but operations all over the United States. We're almost about to the US. We're in London, Tel Aviv, Cape Town, and Berlin, and then we also have other locations to support our service programs and startup weekends. I know some of you are familiar with startup weekend and participated. So that's a very large operation, as you can imagine, supporting 163 countries with fabulous community managers and accelerator programs, supported largely by a team and network of mentors and experts who come in before. So we have rolling applications for our programs. There are no live programs in San Francisco right now, but we have programs in New York, Los Angeles, like I mentioned, outside of the US. There's 26 you can see them on our website. Yeah, happy to answer any questions that you may have.
All right, so yeah, the context here is that we always hear Spark plus Mesos. We hear Spark plus the standalone scheduler. Where's Kubernetes been? What's up? Why did you not come from the Berkeley Amp Lab?
Right, hey everyone. I'm here to talk about Kubernetes and native Kubernetes integration with Spark that we've been trying over the last couple of months. So this is a project that we started in October. And then we started going over different designs for how we could get Spark to talk to Kubernetes directly as a cluster manager rather than the way we currently do it, which is using a standalone cluster which is deployed on top of Kubernetes. So I'm not quite sure how familiar everyone is with Kubernetes here, so I kind of added a little bit of the beginner stuff. A show of hands, how many people are familiar with Kubernetes abstractions, different controllers, pods? Okay, so half the people here, so I'm going to go over the basics anyway. So it's an open source cluster manager. Basically what it does is it lets you manage your applications, deploy them, pretty much keeps them alive, replicates and so on across different nodes. You can set up services which let your applications talk to other applications or out to the internet and so on. So it's a declarative way to manage your applications. And we have a lot of contributors, a lot of commits, and yeah. So this is the high-level overview. You have the Kubernetes master, which consists of the API server and the scheduler. There are a couple of other components, but for now, at the high level, this is sufficient. So the API server is what you talk to create abstractions within Kubernetes in order to create, say, containers, pods, whatever. And the master then talks to the nodes. The master will set up whatever application you want to run on the nodes. And you pretty much, the scheduler is what actually schedules them onto the nodes, but the nodes can pick up stuff from the API server and start running. So it's sort of distributed in that manner. So just concepts. Everyone kind of knows what a container is, I hope. It's a sealed package. Docker is just one of the ways that you can run it, but you have support for Rocket and other stuff too. A pod is the basic unit of scheduling in Kubernetes. You don't really schedule containers themselves. Pods have multiple containers in them. You can have one or more. And typically, like the example here, content syncer and web server, these two are two containers that you want to run together at all times because you want to sync content from somewhere and then serve it out of the web server. So that's typically like two processes that need to run together. So those are two containers that will be in one pod. The controllers, there are many different varieties of them, but basically all they do is to go over your specification that you provide, which will be the desired state, and look at the current state of the system, and then try to reconcile the two. So it's just a reconciling loop, which is going to, if you ask it to bring up pods, then it's going to bring up pods. If you ask it to create a service, it's going to do that, and so on. So there are different controllers for different purposes. And a service is a set of pods that you target and try to control them as a networking abstraction. So that's the service. Pods, like I mentioned, over there you can see the pod has a containers in a pod can actually share that volume, and you can have, for example, with the content syncing container and web server, you could have both of them be containers and they can share the volume, which is sort of use case. So Spark, everyone here knows about Spark. We have a lot of use cases. There's batch interactive streaming and so on. So we want better resource utilization when we run Spark, and that's kind of the goal for our project here. This is the current way in which we run Spark on Kubernetes. It's you set up a standalone cluster on top of Kubernetes, you stand up your own master, you stand up workers, and then launch your jobs. But there's a lot of problems with this approach because well, you have two levels of resource management. So if you were to have a cluster in which you have your serving jobs and then you have batch jobs, and during the night maybe your serving jobs aren't so active because there are fewer users, you want your batch jobs to take up those CPU cycles. That's something that's really hard to do with the current model because you have a fixed number of workers, and to scale that dynamically is really hard.
Can I ask you a question?
Yes.
Why would you use Kubernetes and not Spark on Yarn?
Spark on Yarn is very specific to running the Halo stack, but Kubernetes is more general purpose. It lets you run pretty much all your applications. So we're trying to get to a state where we can confidently say you can run all of the big data stuff, you can run all of the serving stuff, and it's all going to be there, and it's going to share the cluster fairly. So Yarn, in my opinion, is more specific to running Spark and other big data workloads.
See, so do you just have one master controller, or do you have two, or to take care of failure?
In the standalone,
Yeah.
typically it's just one master controller, which is gonna, it's not even a master controller, it's a master pod that comes up, and you have multiple workers which talk to that.
Right, but if the master fails, what do you do?
So pods themselves, from what I remember, I think the example, we use replication controllers, so those are capable of bringing the master back up once it goes, if it goes. So we started looking at external cluster backends, and there are already three of them. There's standalone mode, there's Yarn and Mesos. So we thought of adding a Kubernetes client and cluster mode to that, which will live within the Spark project. So how it would really work is very similar to how you might use Mesos on with Spark, which is in Spark Submit you pass in the URL of the master, and that's going to launch both executors and the driver into the Kubernetes cloud. But for now, because of other challenges with Kubernetes, we decided we should start with cluster mode support. The driver will be running within the cluster, and it will be responsible for spinning up the other executors and doing the tasks assigned to it. So cluster mode, in case someone's not familiar with it, it is when you have all components of the Spark job running within the cluster, and Spark Submit is on the client side, which is on the user's laptop or whatever, and that's going to go ahead and just launch stuff onto the cluster, and then it's going to run in the cluster from that point.
So, yeah, I thought your question was about Kubernetes master,
Yes.
not necessarily the Spark master.
No, Kubernetes.
So, yeah.
Okay, in the context of that, yeah, the Kubernetes master, you can replicate different components, and you can have active, passive, or even have like HA configuration in there.
Right.
So,
Is that pretty well defined? Is it well documented? I mean, are there
yes, multi-master components are. So
even across, that would be more. Is it across cloud providers as well too? The federated?
Oh, the federated thing?
That's something.
That is still in progress. I don't think we have a recommended way of doing that yet. But as for the general multi-master in one region and so on, that's pretty well done.
Because you get the split rate problem.
Yeah.
So that's a painful thing to do.
So because our storage backend is etcd for all the configuration, and that's strongly consistent, so kind of avoid a lot of the split ranges in our program.
Yeah.
So this is the progress so far. We're in phase 1, which is the static allocation MVP. So with static allocators, you're going to be like, hey, give me 5 worker nodes, or rather, give me 5 executors, and it's going to spin up 5 executors, but you're not going to be able to scale it up and down. So it's not so much better than the standalone model. But in phase 2, which is what we hope on tackling next, we hope to get dynamic allocation support so that you can, for a long running job, you can have it go up and down the number of executors and the system is going to scale. Spark is going to make your job scale accordingly and talk to Kubernetes. So this is for communication, we're using from the Spark end, there's Fabricate's Kubernetes Java client. Because a lot of Kubernetes stuff is basically REST implementation, there's a REST interface in the API server, so you could pretty much hit that and get any of the details from the system. So it's easy to use client library, and pretty much all of our work is done in Java and Scala. And this is, as opposed to, I think, the Mesos model, which has a shared object that needs to be mounted and so on.
So Fabricate, that's by the Red Hat guys, right?
Fabricate, I think, is its own company. I'm not sure. Yeah, so in the Kubernetes job, when you're submitting it to the Spark, using Spark Submit, you have a bunch of other options that you might have to provide. Some of these are like the driver image and the executor image, which could be different if you really wanted them to be. The certificate and the client key files, these are more for authenticating to the Kubernetes API server and talking to it and establishing. The service account name is going to decide what privileges you have on that cluster, like if you can create pods, if you can create controllers, so on. And uploads, so on. These are just a standard set of options. And then labels, you can specify a custom set of labels for your driver pod. And that lets you maybe expose just your driver to a different service and just use Kubernetes rather than if you ever found the reason to do that. So for dynamic executor scaling, this was the thing that we were designing initially. So initially we thought maybe use a replica set because it's kind of idiomatic from Kubernetes end, and you can have a replica set of executors and keep scaling them up and down with Kubernetes. But then we realized that this doesn't work because when you try to scale down the number of replicas in a replica set, the replica set does not have any knowledge of your Spark application, so it's going to kill some random executor. And you don't want that because Spark can make a better decision about which executor to kill. Spark knows which executor has cached the least amount of data and picks that to kill. So we decided to go with just pods. We have a driver pod, and that is in turn going to create other executor pods directly. It's not going to create a controller or use any of the other Kubernetes controller abstractions. So this is pretty much how the flow is. First, the user hits Spark Submit, and that goes to the API server. The API server is going to schedule a driver pod. The driver pod then authenticates to the API server again, and then asks it to create a bunch of executor pods. And the scheduler then schedules those executor pods. These are all on possibly different nodes or the same node because it's container-centric. You don't really care where it's running. And then your application starts up, and then you have back and forth communication between the executor and the driver. And eventually, when you're done with it, the executors are cleaned up. And the driver still persists in the system because there's typically logs that you want to read from standard out of the driver. And that is something that you can again hit the API server for. It's pretty similar to Yarn in that we can do kube control logs to get the stream of the entire master logs. And I couldn't do the demo because of the laptop issue, but I did record a video, which I recorded it just now, so it's the same thing.
Yeah. But did you just do that?
Yeah.
And emailed it to you or not emailed it? That's awesome. It's important to know, so with like Mesos currently, like you can ask for cores and things like that. Like, can you do that with the current version? Or is it's at the level of just a worker? You can ask for another worker. Like do you ask for more cores or?
You can ask for a custom number of cores, yes. That is possible even now. The difference would be you cannot dynamically expect it to scale. That is a piece that is missing.
Yeah, because that's always confusing me because I think of Kubernetes as more an orchestration framework, but not necessarily find a
blue now. This looks okay. Monitors look good. We can see the rest of
The
them.
monitor?
Monitors look perfect, yeah.
Oh.
Yeah, definitely. So anyway, the options that you pass to it, and I'm monitoring the same application using the queue control dashboard as well. So we'll just see. It's Spark Submit is actually submitting a local set of jars, or just one jar actually. The Spark Pi is what we're trying to run. And you can see that the driver just started up. And once the driver starts up, it warms up, and it's, depending on the number of executors we requested, which is 5, it's going to spin up executors. And you can see that it's started registering the executors that have come up, and then we'll start processing. This is queue control logs. We're tailing and streaming the log from the driver. So I think there are like 10,000 tasks in this one. So if you were to go to the Kubernetes dashboard, you can actually see each of the executors and drivers. In future, we actually want to add in third-party resources which would show up as first-class workloads, so that you would have a Spark job workload, and then you could have all of your Spark jobs listed under it, and direct access to the Spark master UI as well. So that's in the works.
Yeah, I thought Fabricate has kind of a dashboard. Probably not.
We're not using Fabricate the rest of the system. We're just using their Java client to access, to talk to Kubernetes, and that's it. So it's just a dependency that we added to Maven to say, just take that job. So you could actually go into the driver from here and see that it actually yeah, so pi is roughly that figure. So that's the okay, so the next part of the challenge for us, especially with dynamic executors, is the shuffle service. We need the shuffle service is a component in Spark which takes care of keeping the files which the executors have computed alive and around past the lifetime of the executor. So especially in a dynamic execution case, when executors are being scaled down and being brought up, you don't want to recompute that data just because your executor is cleaned up. So you typically put that into the shuffle service pretty much handles all the data. So we came up with 2 different designs for the shuffle service. Both of them have their pros and cons. One of them is daemon set. Daemon set is an abstraction in Kubernetes that lets you say put one copy of this pod on every node. So typically for the shuffle service, we would be like run one pod called the shuffle service pod on every node, or a set of nodes which are selected by a certain selector. So this is sort of idiomatic in that Yarn and Mesos would probably run it this way. The shuffle service would be a shared resource. It would share disk from the other pods and so on. But there are issues when doing this because there's not enough isolation. There are lots of different processes which want to access the same storage. And we really don't want this because pods themselves are not meant to share disk between pods. It's only containers within pods which typically share disk in a read-write many fashion. So the other alternative that we have is to do a per executor shuffle service, which is to co-locate each executor pod with the shuffle service itself. So in this model, it sort of becomes like the nodes of this Spark cluster become the pods themselves. But the downside of this would be that the shuffle service is replicated in a lot of places, and even the same node, you can see there are 2 shuffle services, so you might end up with more than one shuffle service per node. But the upside is you get good isolation guarantees, and it's super easy to expose it on the pod IP, considering pods are given an IP address in Kubernetes.
Wait, so would you, because that's almost back to the from the executor, can like foo1 die and that shuffle service continues to live?
Yes. So foo1's resources would be cleaned up and the shuffle service would continue to exist. Yeah. And the shuffle service itself is not too heavy on resources. In terms of like, it's not going to consume so much CPU as it's going to consume disk. There's some work to be done in terms of C groups and who exactly gets charged that disk and so on. So, but otherwise, yeah, this is an easier model to use for us because it fits in with the kind of things that Kubernetes does. And there's a lot of work on resource allocation that we're thinking of doing. There's right now we have 3 very coarse QoS levels, which are like guaranteed, which is you ask for so many resources, it's a hard limit. Say I ask for 100 megabytes, I'm going to get 100 megabytes on that node, and I'm not going to get preempted. And if I cannot get 100 megabytes on that node, I'm just not going to launch. It's going to pen schedule. Burstable is you set a minimum limit, which is how much memory you actually want, and you can let it burst above that limit. If you have excess CPU resources, or maybe you have memory lying around, you could just let the job use that. And best effort is more like you don't specify any limits. It's going to use as much as it can, but if some guaranteed job were to come by, it can actually preempt your task, which is best effort. So right now, we just specify the driver and the executors as being guaranteed. But in future, we want to do it so that there's different queuing mechanisms, and then we want to have best effort and burstable pods, so that you can have batch jobs which are long running, which could maybe get preempted by your serving jobs, but can burst during times where there's idle cycles. So yeah, another challenge is to schedule them fairly, schedule all the Spark jobs fairly across different namespaces, across different users, and so on. So we would need more than just the current granularity of specifying best effort guaranteed. So that's something we're working on. And third-party resources, like I mentioned, we want to be able to say queue control get Spark job and just get the set of Spark jobs and associated pods with it. So this would give us give Kubernetes a high-level sort of overview of all the Spark jobs running in the cluster, including, like for example, the third-party resource could actually contain the number of executors or more Spark-specific fields. So that gives Kubernetes a way to deal with Spark, and Spark a way to deal with Kubernetes the way we just spoke about. So, yeah, so their contributions are welcome. There's about 7 of us working on this now, and we're hoping that more people will come by, people with expertise in Spark performance measurement and just general Spark expertise. So I'll put up the slides, I'll send them over to Chris and Fregly.
So those are some big names up there. Andrew Ash and those guys, really?
Yeah, they've been pretty active in contributing to this stuff. We've had a lot of activity since we moved to our own branch. We've been speaking to the Spark committers as well, and the current thinking is we're going to maintain the fork for a while, and then eventually it's going to get into Spark upstream. We're going to release a tool.
Yeah, that guy Tim Chen, he's the one that was supposed to speak but got sick. But so I think he was pretty much the main Spark Mesos guy. He worked for Mesosphere, solving these same problems for.
Yeah, he's been super helpful in all this. Yeah, it's a little different considering Kubernetes computation model is different. So the problems that we face are sort of but it's really nice to have Tim on it.
You know, when I started a Spark instance for any of my jobs, I started to go for big single node workers, even if I can, for during the shop, I don't want node-to-node communication definitely between JVM and even less between different machines.
I'm starting to see that. Yeah, that pattern more and more. Like there's, yeah, so Netflix actually does something similar, but they spin up an entire cluster per job, or like Amazon cluster. So, but it like helps with like debugging and just trying to reason through the job and yeah, the inter-node communication. Yeah, how big are these nodes? I mean, are they big as 128?
They're pretty big.
Yeah. Oh, yeah. This is on premises.
So the focus here is on running serving jobs and other kinds of workloads in addition to Spark and big data workloads, and to run them in the same cluster. So that is where this will have the most benefit. Because you will be able to.
Which I will face because I want to eventually run more than just the job. And eventually there's going to be more jobs running, so I don't know which machines are going to be allocated. So I might need to share my memory space or my CPU space also. Right? So I don't know in advance how much it's going to be. Like I said, it's like a fragmentation for like a fragmentation problem, right? How much do I have available on each of the nodes whether it's my spread.
I see. So you're talking about bin packing and putting the resources in such a way that there's always fragmentation basically.
Yeah.
I think that's a general scheduling problem, and that's the way to deal with it